Hi, welcome to another video. So hopefully this is a quick one. It's a bit of an add-on to the last one I did, this analog devices waveform generator. So I think I forgot some of the code in the last video. Let me quickly show you what I was doing and why I wanted it. So I test these Mackie amplifiers. I repair them. This one had a blown switch mode power supply, and this Keysight oscilloscope, it's got a fantastic waveform generator. You have to pay additional money, but you, let me show you. Sine wave, square wave, ramp, pulse, DZ and noise. So it's far superior to this analog devices. Well, it costs a few £100 for the software. But when I want to change the frequency, I have to adjust the frequency, wait a bit and start adjusting it just to test the response of this amplifier. So I thought if I get this analog devices, simply program it with microelectronica software and I can do what I want. So before I turn on the scope, I've got it set to 10-second sync at the moment. Let me just show you the code what I was doing. I didn't show you the other day. So you remember we start the chip and reset it, and then you write the low frequency bits and then the high frequency bits. So instead of writing the number, I believe the 400 Hertz was 50C7X, I just put an int there, so we've got a total, and up the top, the total, see if I can zoom you in a bit. I haven't got time to start doing a screen capture. So the total equals the frequency register, which you remember bit 14 is 1, ORed with, so that vertical line, ORed with the frequency 1, which I've set to 30 Hertz initially, and just those first 14 parts. So any more, if the frequency starts going above 14 bits, is not going to interfere with the 4000, which is this frequency register 0, least significant byte. Remember there's bit in 14, can't touch that, so I can't let this overflow and start running into the 4000 here. And then frequency 2 is 4000 plus frequency 2. Now frequency 2, because it's the second part of a 28-bit register, it's going to take forever to get up to 12.5 megs. So I haven't, divided any of the bits. So that's how I got total frequency reg ORed with the frequency, which is 30 Hertz. If I scroll up a touch very quickly, so remember I got it working using the frame sync as opposed to the regular SPI. And so frequency register 0, 4000, and that's frequency 1, 41C. Which is 30 Hertz. In my while 1, we write the 2100, write the total, which starts incrementing, total 2, but not doing anything with the phase, leaving it 0, and to exit, just write the 2000, which is a sine wave, and remember 2020 for square, 2002 for triangle. And then down the bottom, frequency 1 equals frequency 1 plus hex 6b, which is an increase of 10 Hertz. So if the frequency 1 gets to 14 bits wide, 14 bits long, the frequency becomes 30 Hertz again, starts counting again, but frequency 2 equals frequency 2 plus 1. So that's where the most significant bit starts counting up in ones. And for this demonstration now, I've got a 1600 millisecond delay, so 1.6 second delay. So let me put it into practice, running that sine wave into this repaired Mackie amp and then watching the response on the scope. Now the reason I did this, I repaired an amp for someone a while ago and he said the bass response wasn't the same as the other amp, his other amp. Now I repaired, I think it was a version A, or one of the first. His other amp was a version D, so there's slight differences anyway. But let me show you. So this is ready. I've got it 10-second division. I'll turn on the chip. So I've worked with a few of these Mackies. So that's 30 Hertz, 40, 50, 60, peaks at 60, and then 70, 80, 90, and so on and so forth. It actually rounds off about 400 Hertz and then creeps up a bit at 900 Hertz, and then once you're over 1000 drops right off and doesn't really do much after 2 kilohertz. So this is just the bass response. Now these little lines you might be able to see are actually, because this doesn't ramp automatically and I'm having to communicate with it, this is actually the data for the communication coming through, and it's obviously at different frequencies able to amplify those more. So we're nearly up at how many? 10, 20, 30, 40, 50, 60, 70, 80, 90 seconds. Right, and it's finished. So I can now, actually it is plugged into the computer, capture that, do a printout, and so I know that bass response, that curve, spot on. Now, because I want to concentrate on 1 kilohertz and leave it there, I've taken off the wire one. It's just going to write to the chip once. It's going to give me 1 kilohertz. So I've taken out those total bits, and that's the frequency for, or that's the hex number for 1 kilohertz. And then I'm not incrementing the second one either, so that's 4000, and taken out the brackets down the bottom, so it's not in the wire one anymore. So it's going to do all that once and that's it. Right, so there we are, as near as, damn it, 1 kilohertz. So there is a bit of jitter, but because this is the bass part of the amplifier, this isn't quick enough to see that jitter. And now I'm able to just sit back and let the frequency rise up. I thought, well, I'll put 1 scope on the bass and 1 scope on the treble output. So these are both 4 ohm resistors. That bass one's 200 watt, 4 ohm, and this is, what was it? I think 4 ohm, 100 watt. This one gets hot, so it's sitting on a glass. So now if I turn this second channel on, as I was ramping up the frequencies, this obviously, the treble in green doesn't do anything sort of below 1 kilohertz. It sort of starts peaking at 3.8 kilohertz, and again at 16. And obviously this bass, which is the yellow one, drops off 15 to 2 kilohertz, and there's nothing at 3 kilohertz. But I noticed, if I make this bigger, you have to excuse the noise on the treble. So that's turning the amp up and down. So both these outputs are with respect to ground or virtual ground. There's a few low value resistors. And you see there, the treble isn't actually in phase with the bass. I'll turn the amp down a bit. This is actually being amplified through the amp now. So you see the bass here lined up on these marks, these lines, there and there. So this treble is actually nearly 180 degrees out of phase. If it's 180, it should be in the middle of this square, but it's just to the left. And I was looking, I thought, that's 200 microseconds a division. So 200, 400 microseconds. And I remember looking at Mackie's circuit drawing. If you've ever repaired one of these amps, there's spaces here for 2 more op amps, and each op amp has got 2 stages inside, so they did nothing but cause 170 microsecond delay. But now they're actually bypassed, and there's various resistors here, the sort of feedback resistors, are 0 ohms, so they're just bypassing these 2 chips. So bypassing 4 stages which is effectively putting this bass out of phase with the treble. Now, if the treble's 180 degrees out of phase, I guess you swap the wires on the horn and bring it back into phase. But it's not totally 180 degrees out of phase. So I'm guessing in the early days someone wanted the treble in phase with the bass, because this bass, because it's got various filters for the low frequency and it's got band amplification and bottom end amplification, sort of 60 to 120 hertz, the bass goes through more chips than the treble. And maybe you know, maybe you don't know, anytime you go through one amplifier, there's a propagation delay. So because there's 2 amps inside these op amps, you've got twice the delay. And you can select various amps and actually get an amplifier to give you a specific delay. If you don't want delays, you just spend more money, get faster chips. So obviously the root of any good amplifier is to have the bass in phase with the treble. This noise here is actually the jitter on that analog devices crystal. Nothing to do with analog devices, it's the crystal on that cheap board from eBay. And the treble is quick enough to see the jitter. The bass, having a lower frequency response, isn't. So yeah, Mackie amplifiers, they've taken out a couple of op amps and reduced the delay. So as I was saying, every amplifier I've seen, every Mackie amplifier, SRM450 V2, these 2 chips have never been populated. Some of these capacitors, these I think the polystyrene, are actually over £1 each for these surface mount, or good quality ones anyway. So if they put those 2 chips back in there, give us 170 microsecond delay, that would actually, we got 200 microseconds out there roughly, so that 170 would bring that more in phase with the treble. Which begs the question, have they just deleted the chips to save money? Because it's a sort of PA speaker, are you really going to hear it? But it doesn't matter if you're really going to hear it, it's going to be better. Or maybe they just figure, I'll swap the horn around and I'll turn it out of phase, which might bring it more into phase with the bass. Anyway, it's just an observation, nothing more than that. Hopefully this video has given you some insight to, the phase, matching the phase on the bass and treble, and delays on op amps. Have a look, propagation delay at op amps, you might learn something if you don't know already. Thank you very much.